What would happen to you if you suddenly found yourself in a four-dimensional universe? Some of you might say, wait, we already live in a four-dimensional universe with 3 spatial dimensions and 1 dimension of time. Others will recall string theories where our universe might have 10 or even 11 dimensions. But right now, I'm not talking about that. I mean 4 full-fledged macroscopic spatial dimensions. A universe in which, in addition to the ability to move forward and backward, left and right, and up and down, there is also another perpendicular direction. Just thinking about it makes your brain hurt. And that's no surprise. You've probably heard more than once that we, 3-dimensional beings living in a universe with 3 macroscopic spatial dimensions, simply aren't equipped to understand 4-dimensional space. But that doesn't mean we can't try to imagine it and ponder what would happen to us in such a universe. And that's exactly what we're going to do today. We'll try to find answers to many questions related to the 4th dimension. What would we see if we found ourselves in a 4-dimensional universe? What are the capabilities of 4-dimensional inhabitants of this hypothetical universe? And how might they perceive us? What if we could manipulate the 4th dimension? Could we survive a transition into 4 dimensions? And what if our universe suddenly became 4-dimensional? We'll talk about all this and much more today. I'm Andrei, and this is Cosmos Elementary. In fact, scientists, mathematicians, and philosophers have been thinking about dimensions beyond the 3 familiar spatial ones for more than 100 years. This idea has been seriously considered in science for more than 100 years. In 1921, Theodore Kaluza published his multidimensional theory of gravity, in which he used an additional spatial dimension, although it was a very small one. Today, this theory is known as Kaluza-Klein theory. Since then, the idea of higher dimensional spaces has been considered many times. The most famous modern example is, of course, string theory in its various versions, including M-theory. As many of you know, it can have as many as 10 spatial dimensions. Again, these dimensions are curled up and very small, which is why we don't see them. It's important to remember that the existence of these additional dimensions is far from proven. In string theories, they're needed for the mathematics of these theories to work. However, experimentally confirming or disproving their existence is something we're not yet able to do. And yet, there are experiments in which scientists try to test the existence of extra dimensions. If not 6 or 7, then at least 1. For example, an extra dimension could affect the behavior of particles at very small scales. However, so far, there are no definitive conclusions even here. Also, I have already talked about extra dimensions in the context of the brain world idea. I made a separate video about it. The idea there is that our 3-dimensional universe is a subspace within a multidimensional hyperspace called the bulk. And then, alongside our universe, there exist other parallel universes. And this, for instance, is how they try to explain the weakness of gravity compared to other fundamental forces. The idea is that it might leak into other parallel dimensions. Additional dimensions are actively used in calculations, models, and various theories. But their actual existence, whether on microscopic or macroscopic scales, remains an open question. Maybe we don't have an additional 4th macroscopic spatial dimension. But somewhere in the multiverse, such universes do exist. Today we will try to understand what our interaction with the 4th dimension could be like. And even though I've clarified this many times, let me emphasize once again, when I talk about the 4th dimension, I specifically mean a spatial one. I'm not counting time here. One-dimensional space is represented by a line along which we can move either in one direction or the other. Two-dimensional space is a plane. There we can move forward and backward, as well as right and left. In our familiar 3-dimensional space, volume appears, and an additional possibility to move up and down is added. So far, with each step, we've been adding one perpendicular axis. Accordingly, to move into four-dimensional space, we need to add one more possible direction of movement, perpendicular to the three familiar axes x, y, and z. And here it gets tough. It seems completely absurd to us. But interestingly, we're capable of doing much more here than just throwing up our hands and saying, "What the heck is this?" We can quite possibly, if not visualize it, then at least describe it in words. How a four-dimensional being would perceive our universe. And conversely, what would happen to us in a four-dimensional universe. Analogies are a very useful tool for understanding spaces and shapes of different dimensions. It should be said that they are often used for greater clarity, even when additional dimensions are not involved. For example, the fabric of space-time and its distortion is often depicted as two-dimensional grid. It's not that a three-dimensional grid could not be shown. It certainly can, but a 2D representation is simpler and conveys the essence more clearly. It is a similar story with the geometry of the universe. When people talk about the shape of the universe, it's not easy to imagine how space curves on a global scale. For example, in the case of a universe with closed geometry, it is difficult to picture how three-dimensional space can curve back on itself. Yes, this can be described in words. Imagine you're flying through the universe in one direction and eventually you return to the point where you started. However, visualizing this in 3D is already difficult. That's where we use an analogy, showing this with a two-dimensional spherical surface. I'm sure many of you are gamers, and for many people, 2D and 3D are strongly associated with games. By the way, imagine this, four-dimensional games also exist, and I'll even show you some of them a bit later. One of the first video games I've ever played was Super Mario Bros. Such games are called two-dimensional, not because the image on the screen is always two-dimensional, but because the character in these games can only move along two axes. They cannot move into the depth of the image. Still, visually, such games would look quite familiar and obey the laws we know. A true two-dimensional universe would look completely different to us, three-dimensional outside observers. And this is excellently described in Edwin Abbott's book Flatland, which was published back in 1884. Since it's still a work of fiction, it of course contains some simplifications and inaccuracies which I will mention later. This book will also help us understand how our universe might look from a four-dimensional universe. Flatland, as you can guess from the name, is a two-dimensional universe. The inhabitants of this universe are various two-dimensional geometric shapes: triangles, squares, pentagons, hexagons, octagons, circles, and so on. The main character of the book is a square. How do you imagine life in such a universe? When we look from the outside at a two-dimensional game, we see the game world, characters, terrain, and objects. But have you ever tried to imagine what the characters in the game see? Some of you might imagine something similar to what you're seeing on the screen now. A recreated classic Super Mario with a first-person view. By the way, this is a working game and I'll leave a link to this in the description. Here Mario sees perfectly three-dimensional objects, but his movement is limited to two dimensions. It's as if he's trapped between two glass walls. Still, the world he sees is generally familiar to us. But naturally, inhabitants of a true two-dimensional universe wouldn't see anything like this. Volumetric shapes couldn't exist in a universe without volume. That's why the inhabitants of Flatland see each other simply as lines. They actually see everything as lines or points. The question then is, how do they distinguish each other? After all, in the world of Flatland, your social status depends on your shape. Figures of lower social status engage in, feeling each other up. The idea is that by touch they can determine how many angles the other has and what kind they are. They also identify each other by voice, but still partially visually, thanks to the fact that in Flatland there is fog. The farther a figure is from the observer, the more it fades into the fog. So Flatland basically is a flat Morrowind? In general, this creates a kind of gradient that allows one shape to be distinguished from another. Here, how it is illustrated in the book. There's also a pretty good demonstration on Wolfram. And of course, there are colors too. But with this description, we run into the first problem. For all this to work, and for even the lines to be visible, they must have thickness. And thickness, in this case, would be a third dimension. Here we should remember that this is a work of fiction, and without some assumptions there would be neither a plot nor other good analogies. The book also contains description of universes with different numbers of dimensions. For example, the main character first visits the one-dimensional universe called Lineland, where all the inhabitants live along a line and are doomed to spend their entire lives between two neighbors, since there's no way to go around them. It's like if Mario lost the ability to jump and he would be forever stuck between two Goombas. But the real action begins when a guest from the three-dimensional universe visits the square, and then the square travels there and sees his own universe from the outside. This can serve as a pretty good analogy for how we might see our own universe if we found ourselves in a four-dimensional space. So one day the sphere visits the square. But first, how was the sphere even able to do that? Obviously, a three-dimensional guest cannot fully fit into a two-dimensional universe. Therefore, at any given moment, only one layer or cross-section of a three-dimensional figure can exist in Flatland. The book illustrates this like so. But we have better tools available. There is a game called 4D Toys, which demonstrates how a two-dimensional universe inhabitant would see various three-dimensional shapes intersecting with their flat universe. Here, a comparison with shadows is often used. We can form an idea of a 3D figure based on its 2D shadow or projection. And it turns out that a two-dimensional universe inhabitant, a square, perceives a sphere only as a circle. But just as it's difficult for us to imagine a four-dimensional shape, the square struggles to understand a three-dimensional shape and cannot believe in it. The sphere tries to explain and prove this to the square. For example, the sphere begins to move through the two-dimensional space, and the circle visible to the square changes its size, something circles in his universe are incapable of. Similarly, we can't comprehend how there could be yet another direction perpendicular to the three we are familiar with. And the square has the same problem. His quote-unquote brain isn't equipped to understand what a third dimension is. And the sphere tries to explain it to him like this. To turn a point into a line, you need to start moving along one axis so that each next point of the segment does not overlap with the previous one. To create a two-dimensional object like a square, you do the same in the second direction. You need to start moving from the line again in such a way that each new point during the movement does not occupy the position of the previous ones. So far, everything is clear. Next, the sphere says to the square, quote, "Every point of view, that is to say in what you call your inside, is to pass upwards through space." The word upward is unclear to the square, so the sphere clarifies. To pass upwards through space in such a way that no point shall pass through the position previously occupied by any other point, but each point shall describe a straight line of its own. This is all in accordance with analogy. Surely it must be clear to you. And so when we try to understand the fourth dimension, we are in the same position as the square. For him, there is no word for up, and for us, there is no word for the fourth axis. And we too, if we want to turn a cube into a four-dimensional object, must move in such a direction that no point occupies a position previously held by another point of the cube. Here's a more familiar explanation of four-dimensional shapes, which you've probably already come across in various popular videos, articles, and books. There is a line. A square has four edges, each of which is a line. A cube has 6 faces, each of which is a square. And next, there is a 4-dimensional shape called a hypercube or tesseract. It has 8 faces, each of which is a 3-dimensional cube. It all makes sense in words, but it's hard to visualize. But at least we can show a projection. You've probably seen images of hypercubes like this. But here's what's interesting. We can easily visualize what a 4-dimensional shape might look like if it entered our 3-dimensional universe. Just as the square in Flatland could only see a 2-dimensional slice of a 3-dimensional being, because there's simply no room for the 3rd dimension in his universe. If a guest from a parallel 4-dimensional universe were to appear in ours, at any given moment, we would only be able to observe a single slice of them passing through our 3-dimensional space. Once again, the game 4D Choice comes to our rescue here. Let's continue the chain from the Flatland, and imagine that a 4-dimensional hypersphere visits our 3-dimensional universe. Instead of a slice in Flatland, we now see a 3-dimensional sphere. And this is just a slice, or one 3-dimensional layer of the 4-dimensional hypersphere. We can interact with it, move it, and even change the point where the hypersphere interacts with our 3-dimensional universe. Just like in Flatland, where the radius of the circle would change, here the radius of the sphere changes. When the sphere we see disappears, it means it has left our 3-dimensional universe. You can also play around with other shapes, and this is how we would see a hypercube if it entered our universe, or these other shapes. In short, if a 4-dimensional being from another universe appeared, there's no need to worry that we'd see some incomprehensible figure that would blow our minds. Such a being might not be just a geometric hypershape, but could have a more complex form. But we would simply see a collection of 3-dimensional shapes. Another 4D game I found is 4D Explorer, made by a YouTuber Jelly Vermander. Here, interaction with the 4th dimension is interestingly integrated into the gameplay. The parts of the 3-dimensional level are slices of 4-dimensional objects. You need to manipulate them as they change shape, and in this way you must guide the astronaut to the rocket. I'll leave a link to it in the description as well. And this is another similar game. It has been in development for several years now, but unfortunately the release date is still unknown. So far we've talked about how we might observe a 4-dimensional entity in our 3-dimensional universe. But what if, on the contrary, we traveled to a 4D universe? Or how would a 4-dimensional being see our world? The Square still refuses to believe the Sphere's stories about the existence of a 3-dimensional universe, so the guest has one last option left. Not to tell, but to show. And the Sphere transports the Square into its world so the Square can see everything for himself, including his own 2-dimensional universe from the outside. It should be noted that the book doesn't pay much attention to certain details, particularly many physical aspects of how 2-dimensional Flatland would have to exist. For example, how gravity would work there, or how a 2-dimensional being could survive in a 3-dimensional universe. We'll talk more about that later. Once in the 3-dimensional universe, the Square is faced with the infinite plane of his own universe, where he can see everything at once. Literally everything. The book also doesn't devote much attention to describing the anatomy of Flatland's inhabitants. For example, it mentions that triangles have small brains located in a corner, but this is well depicted in a film adaptation of the book. There is a full-length movie from 2007, which is actually available in full on YouTube. I'll also leave the link in the description. So this is what the inhabitants of the Flatland look like when observed from a 3-dimensional universe. We see the brain, and in fact all the internal organs of all the characters. We see everything all at once. This view is immediately different from any 2-dimensional game. With Mario, we don't see his intestines or how the mushroom he eats moves inside him. And that's probably a good thing. 2-dimensional games aren't meant to depict a truly 2-dimensional universe. They are more like a projection of a 3-dimensional world with freedom of movement in 2 dimensions. But a true 2-dimensional universe would indeed look something like this to a 3-dimensional observer. And for the sake of the thought experiment, we assume that someone lives there and that somehow works. Observing from 3D, we see the entire plane of Flatland at once. In 3-dimensional space, an object can be hidden from our view by, say, a wall. But here, everything that exists in this universe must lie on a plane. That's why we see the interiors of houses and the insides of the inhabitants. Nothing can be hidden from the gaze of a 3-dimensional observer. Also, to 2-dimensional observers, a 3-dimensional entity can seem to teleport, disappearing in one place and appearing in another. And in theory, if this 2-dimensional universe exists within a 3-dimensional one, it could even move objects or inhabitants from one point to another through the 3rd dimension. A 3-dimensional being can enter any structure by passing walls. 2-dimensional walls are not a barrier at all for a 3-dimensional entity. It can even manipulate the insides of Flatland's inhabitants. So, how would our universe be seen by a hypothetical observer from a hypothetical 4-dimensional universe? Everything I just described for Flatland applies here as well. A 4-dimensional entity, compared to us, has an additional axis along which it can move. One that is inaccessible to us, just like the sphere compared to the inhabitants of Flatland. Our universe would be completely observable to a resident of a 4D universe, just like Flatland is to us. They would see absolutely everything. For example, if they looked at a person, they wouldn't just see what's beneath our skin. They would simultaneously see the skin, muscles, blood vessels, flowing blood, bones, bone marrow, everything, all at once. And here I'm deliberately not showing the usual anatomical images where, thanks to partial transparency of the layers, you can see bones, organs, and so on inside a person. Even then, it would still look different. All this applies not only to people, but to everything. Any objects, structures, planets and stars, every component and the components of those components, all at the same time. It's hard for us to imagine and would probably be difficult for us as well if we ourselves were to enter 4-dimensional space and see our universe from the outside. By the way, a similar plot is described by Liu Cixin. Our organs of vision and our brains would probably struggle a lot to handle such a flood of information and would experience sensory overload. These 4-dimensional folks are adapted to constantly see this way, but we are not. In fact, if 4-dimensional entities could interact with our universe, they would be like gods. They would penetrate anywhere, beyond any barriers. They would move incredibly fast from one place to another. They would teleport objects from one point to another, though not instantaneously, since the object would still need to be moved along the 4th dimension. But they would disappear in one place and reappear in another. Well, at least for now, we don't see anything like that in our daily lives. Although, maybe a poltergeist is actually a 4-dimensional being. But perhaps you've noticed some problems in all these considerations. So far, we've touched on some aspects. For example, the ability of an observer from a higher dimensional universe to see everything in a lower dimensional one. But we haven't covered others. More precisely, I made a disclaimer like, if we survived, when moving into a 4-dimensional universe. But why might we not survive? Well, first of all, we live in a universe with 3 spatial dimensions. And the number of macroscopic spatial dimensions is one of the key parameters that makes our universe the way we know it, creating conditions in which stars, planets, and life can emerge. A universe with 4 spatial dimensions might work differently. It could be governed by different physical laws. And if we found ourselves in it, would we have to obey those laws? Here's a simpler example. When the square from Flatland entered the 3D world, it gained the ability to move in 3 dimensions. But do you remember what it looked like? Like this. You can imagine that all its insides are squeezed between two panes of glass and stay in place simply because they can't move physically. There is no third dimension. And if this third dimension suddenly appears, wouldn't all its internal organs start to wobble or even spill out into the third dimension? Most likely the two-dimensional anatomy wouldn't take kindly to the three-dimensional space. And the same thing might happen to us if we ended up in a 4D world. Everything we're made of would gain extra degrees of freedom to move. And this would affect not only large scales, like our organs, but also how fundamental interactions work. The particles that make us up themselves would stop working properly. In short, if we were simply transported to a universe with 4 macroscopic spatial dimensions, we would most likely die instantly. The sphere in Flatland would probably have killed the square. Like I said, the book allows for some liberties. But we still have one more question. What about not just ourselves in a 4-dimensional universe, but the universe itself? At the beginning of the video I mentioned that the possibility of additional dimensions is not ruled out, but most likely, if they exist, they are incredibly tiny. So what would happen if an additional 4th spatial dimension suddenly appeared in our universe? There's a good popular science article by Siegel about this. I'll leave a link to it as well. By analogy with how transitioning to 4D probably wouldn't suit our body, a similar conclusion can be drawn about the universe itself. And overall, it all depends on the size of the 4th dimension. If it appears but it's very small, for example, too tiny to significantly affect how fundamental interactions work, we might not notice anything at all. However, the larger the 4th dimension, the stronger its effects. This could lead to the destruction of everything we see and know. Although it all depends on the details. There can be different models. For example, models in which electromagnetic, weak and strong interactions continue to work the same way, but gravity leaks into the 4th dimension. But then, bodies held together by gravity, asteroids, planets, planetary systems, galaxies and galaxy clusters would start to break apart. So no matter how you look at it, increasing and, by the way, decreasing the number of macroscopic spatial dimensions doesn't bode well for us and our universe. Sounds like a weapon straight out of science fiction. And that's something Lu Cixin has already explored too. I won't spoil anything, just read Remembrance of Earth's Past trilogy if you haven't already. I also highly recommend reading Flatland. You can also try exploring games like 4D Toys. Even though we don't see the 4th microscopic dimension in our universe, could parallel 4D universes exist? We can't rule that out. And if one day strange, changing shapes start appearing in the air before you, know that it might be a visitor from the 4th dimension.